Next, we'll look at an algorithm for multiplication. So look at the following multiplication algorithm and think about where these numbers that are recorded are coming from. So pause the video, take a second to look at these numbers and see if you can pick out where those numbers are coming from. This algorithm is called the partial products algorithm, where you multiply and record within each place value. So if we look at the problem again, we have 49 times 85, and we have 4 partial products, 9 times 5, 9 times 80, 40 times 5, and 40 times 80. So this algorithm has us record each of the partial products below and then add the partial products to get a whole product or a total product. So first off, we can start really anywhere as long as we get all of the partial products, but we'll start more like a traditional algorithm and say 9 groups of 5 is 45, then we move over to 80. So 9 groups of 80 is 720. Now we move over to the next digit. So 40 groups of 5 is 200, and 40 groups of 80 is 3,200. And when we add those up, we get 4,165. Here's an area representation for that same problem. If the dimensions of our rectangle are our two factors, 85 and 49, we can subdivide each of those side lengths by place value, 80 and 5 and 40 and 9. And then notice what happens with our whole rectangle. It gets subdivided into partial rectangles. So we have the whole area is made up of partial areas. So we have 4 partial areas, and the dimensions of those are 40 by 80, 40 by 5, 9 by 5, and 9 by 80. You can see the picture of the area model, and notice that the numbers in green correspond to the partial products in the algorithm. So note that the area model is not to scale, but it does reflect relative size among the place values. Also note that the area model does not match well with the standard algorithm, but there is a match between the partial products in the partial products algorithm and the partial areas in the area model. So here's another area model. This one represents 28 times 43. If you look at the entire rectangle, it's 28 by 43 rectangle. And again, we can subdivide the rectangle by place value. The side of 43 is 40 plus 3, and the 28 is 20 plus 8. And so now we get 4 partial areas that make up the entire area. So 20 times 40 is 800, 20 times 3 is 60, 8 times 40 is 320, and 8 times 3 is 24. And when we put all those partial areas together, we get the whole area. So here you can see a picture of that, as well as the partial products algorithm. And notice how the numbers in green match up with the partial products in the algorithm. Again, note that the area model is not to scale, but it does reflect relative size among the place values. So finally, let's look at a problem where the numbers are quite a bit larger. Here we have an area model for the product 34 times 127. So in this case, if we break each of the dimensions down into place value, we've got tens and ones for the 34, but now we have a new place value for 127. We have a hundreds place, a tens place, and a ones place. So here there are 3 digits in 127, and there are 2 digits in 34. So we're going to have 6 partial areas, or 6 smaller rectangles that make up the entire rectangle. So here's a little smaller representation of that, a picture representing the same thing that again is not to scale, but it does reflect relative size among place values. You notice that 100 it's not necessarily 5 times 20 as far as the length of 100, but it is quite a bit larger than 20. And also notice that 4 is still even smaller than 7, and 30 is greater than 20. Also notice again that the numbers in green match up with the partial products in the algorithm. So next we have a couple of demonstrations of the partial products algorithm. The product here will be made up of partial products, and in this case we have 4 partial products: 5 times 7, 5 times 30, 40 times 7, and 40 times 30, because the 7 and the 5 in these two numbers are actually 7 and 5, but the 3 and the 4 stand for 30 and 40. So our first partial product is 5 times 7, which is 35. Next we have 5 times 30, which is 150. Next is 40 times 7, which is 280. And finally 40 times 30, which is 1,200. And then we add up our partial products for a result of 1,665. Here's another example of the partial products algorithm, this time for 64 times 283. Our approach again will be write down all of the partial products and then add them up for the total product. So first we have 4 times 3, which is 12. Next, 4 times 80, which is 320. Next, 4 times 200, which is 800. And now we move on to the 60. So 60 times 3 is 180. 60 times 80, which is 4,800. And finally, 60 times 200. 6 times 200 is 1,200. So 60 times 200 is 12,000. And when we add those up, we end up with 18,112. Next, we look at division, and first we want to model with base 10 blocks and look at the meaning of division with concrete objects. Our first example is 437 equally shared with 3 people. So if we model 437, we don't need a place value mat for this problem because we're just going to take 437 and equally share it among 3 groups or 3 people. So the first thing we would do here is start to deal out or divide up the 437 equally among the 3 groups. So maybe first each person gets 100. So now there's 3 groups of 100. Next we're going to have to break up that last 100 so we can redistribute those. So we regroup 100 as 10 tens. And now we can pass out some more. So let's say each person gets 30. So that represents 3 groups of 30. Next we have more to give out. That's each person gets 10. So that's 3 groups of 10. We need to regroup 110 as 10 ones. So each person gets 5. That's 3 groups of 5, leaving us with 2, and we can't equally share the 2 among 3 people, so we need to look back and say that 437 equally shared with 3 people. Each person got 100, then 30, then 10, then 5. There were 145 for each of the 3 people, with 2 left over, or a remainder of 2. If you look at this problem from an abstract perspective, this is a record of what actually happened with the materials. First, we took away from the 437 3 groups of 100, leaving us with 137. Next, we took away 3 groups of 30, which was 90, leaving us with 47. Next, we took away 3 groups of 10, which was 30, leaving us with 17. And finally, we took away 3 groups of 5, which is 15, leaving us with 2. And because we didn't have enough to continue to distribute among the 3 groups, we knew we were finished. And we had to look back and say, well, how many did each group get? And that was 100 plus 30 plus 10 plus 5. So 145 with a remainder of 2. So now let's think about how this would change if we do a measurement division. So the problem, 12,345 divided by 23, conceptualized as measurement, is how many groups of 23 can I make from 12,345? Consider this script of the partial quotients algorithm and a demonstration of the algorithm. How many groups of 23 can I make from 12,345? I know I can't make 1,000 groups of 23 because that would take 23,000. But I do have more than half of 23,000 to work with. Double 12,345 is more than 24,000. So I think I could make 500 groups of 23. That will use 11,500 because that is 1/2 of 23,000. And I only want 500 groups, not 1,000 groups. If I subtract 11,500, there will be 845 left. I know I can do 10 groups of 23 because that would only be 230, and I have 845 still left to make groups of 23 from. Looks like I could make 20 more groups of 23. That would use 460. I just doubled the 230 from only 10 groups. Subtract to find that there are 155 left. I think I can do 6 groups of 23, which will use 138 from 6 groups of 20, which is 120, and 6 groups of 3, which is 18. Subtracting, there are 17 left, so I know I can't make any more groups of 23, so I'm finished. One thing to note is that if you're considering the problem in terms of measurement, the division question seems much more natural. So for this problem, 12,345 divided by 23, for sharing, the question is, how many does each of the 23 groups get? Or how many is in each of the 23 groups if I share 12,345 equally among the groups? But the measurement question seems to, at least for me, flow much more naturally. 12,345 divided by 23 means how many groups of 23 can I make from 12,345? And the process of the division algorithm, just like if I was using real materials, also flows much more nicely for me and for many children. So we finish off with several examples from the measurement perspective and from the sharing perspective. So the first thing we need to do, once we've decided that sharing is the way that we're going to look at this division problem, and that's your choice, either sharing or measurement. But if we've decided on sharing, then this question is asking, if I have 6 groups, how many is in each of the groups? So I start off with 914, and I'm sharing that equally among 6 groups. Right away, I know I can give each of the 6 groups 100 because I have more than 600. So that's 6 groups of 100. So I'm taking away from this 914, 600 to distribute among the 6 groups. And I'm left with 314. And notice that if 6 groups of 100 is 600, then 6 groups of 50 will be half of that. So 6 groups of half as many will be half as many as 600 groups of 100. 6 groups of 50 will be 300, leaving us with 14. So I've given each of the groups 50. Well, I've given each of the groups 100. Now I've given each of the groups 50. And I'm left with 14 to distribute among the 6 groups. So now I know I can give each of the groups 2. That eats up 12 from the 14 that I have left, leaving me with 2. And now I know I'm finished because I can't give each of the groups anymore. We want to look back and say, well, how many did each group get? Well, each group got 100, then each group got 50, then each group got 2. So 152 is our quotient. So our answer is 152 with a remainder of 2. Our next example for the partial quotients algorithm will be from a measurement perspective. So we're going to take the same problem we did before, 914 divided by 6, but we're going to think about this in terms of measurement instead of sharing. So if we interpret this problem from a measurement perspective, what this problem is asking is how many groups of 6 are in 914. So right away, I know that I can get 100 groups of 6, which is 600, leaving me with 314. Now, if 100 groups of 6 is 600, then 50 groups of 6 is 300, leaving me with 14. So again, big picture, I'm making groups of 6. I'm taking those groups that I've made away from 914 and seeing how many more I can make until I can't make any more groups of 6. And at this point, with 14 left, I can see I can make 2 groups of 6, which is 12, leaving me with 2. And now I know I'm finished with the process because I can't make any more groups of 6. So now I just have to go back in and add up how many groups of 6 I've made. I have 100 and 50 and 2, which is 152, and I have a remainder of 2. I'm thinking about this problem in terms of measurement division. So the interpretation of this problem is, how many groups of 8 can I get out of 9,471? So I'm going to be making groups of 8 and then seeing how many groups of 8 I can make and take those away and see how many more I can take from what's remaining. So I'm going to be subtracting off groups of 8 from 9,471. And I can do so efficiently or inefficiently, and this algorithm doesn't really care how efficiently I take away groups of 8. I just have to keep track of how many groups of 8 I've taken away. But I can look at this problem and see, well, if I've got more than 9,000, that means I have more than 8,000, and 8,000 is 1,000 groups of 8. That's 8,000 that I could take away, leaving me with 1471. And now I'm not going to try to be as efficient as possible, but I can take away 100 groups of 8. So 100 groups of 8. I'm writing GO instead of groups of. So that's 800, leaving me with 671. Well, at this point, if I know that 100 groups of 8 is 800, then 50 groups of 8 is 400. Leaving me with 271. So I know that 30 groups of 8 is 240. So I could take away 30 groups of 8. 240, leaving me with 31. And now I have just a multiplication fact. How many groups of 8 are in 31? Well, I know I can get 3 groups of 8, which is 24, leaving me with 7. And I know I'm finished because I can't make any more groups of 8. So now to answer the original question, how many groups of 8 can I make? I just go back and look at all the groups of 8 that I've made. So I can just start adding 1,000, another 100, 50, 30, 3, so 1,000, and then 183. That's how many groups of 8 I can make. And then we have to keep track of the remainder. So 9,471 divided by 8 is 1,183, remainder 7.